So what happens when you take two of the biggest mysteries in the entire universe and just smash them together? Well, that's exactly what we're diving into today. Some theoretical physicists ran this incredible thought experiment where they put all-consuming black holes right in the middle of a sea of dark matter. And the goal? To listen for the song their interaction might create.
All right, so here's our game plan. First, we're going to get a feel for our two main players. Then, we'll look at how you even build a black hole for a simulation, because it's not as simple as you'd think. After that, we'll actually listen to how these things ring, check out their appetite, and wrap it all up by figuring out why this super theoretical research could completely change the game for real-world astronomy. Sound good? Let's go.
Okay, so let's set the stage. Before we get into the nitty-gritty, we really need to wrap our heads around just how weird and how kind of empty the universe we live in actually is.
So take a look at this. It's kind of mind-blowing. Everything you've ever seen, touched, or even heard of, the stars, the planets, you, me, all of that is what we call ordinary matter. And it's only 5% of the entire universe. Just 5%. The rest is, well, it's a mystery. A whopping 68% is dark energy, pushing everything apart. And that other huge chunk, 27%, that's our star player for today, dark matter. It's the invisible stuff that acts like cosmic glue, holding entire galaxies together. And the crazy part? We have absolutely no idea what it is. So this really sets up an epic showdown, doesn't it? On one side, you have the all-consuming black hole, a gravitational monster. On the other, you have the invisible, mysterious dark matter that literally shapes the universe. The question these scientists asked is the one we're all thinking. What actually happens when you put one inside the other?
Okay, so how on earth do you even start to study something like this? I mean, you can't just grab a black hole and some dark matter. It turns out you can't even use the standard textbook model of a black hole because, and this is a big deal, it has a fundamental problem that basically breaks physics.
So the big problem with a standard black hole is this thing right at the center called a singularity. It's a point of literally infinite density. All the known laws of physics just completely fall apart there. It's a dead end for math. So, to get their experiment to work, the physicists had to use a clever workaround. They used what are called regular black holes. Now, these aren't necessarily what exist out there in space, but they're brilliant theoretical tools that get rid of that pesky singularity. They smooth out the center so the math doesn't break down. And you know, good scientists are thorough. To make sure their results weren't just some weird quirk of one specific model, they didn't just use one. They used 3 different kinds of these regular black holes: the Hayward, the Bardeen, and the Ion Beato-Garcia models. Think of it like triple-checking your work to see if the answer is always the same, no matter how you calculate it.
All right, so they've got their custom-built black holes ready to go. Now it's time to set up the lab. But forget about glass beakers and Bunsen burners. This whole experiment takes place inside a computer, built purely out of mathematics and powerful simulations.
The whole process was actually pretty straightforward, conceptually at least. Step 1, pick one of your black hole models. Step 2, dunk it, mathematically speaking, into a pool of perfect fluid dark matter. Now, this is just a simplified model that imagines dark matter as a smooth liquid. Step 3, give the black hole a little poke. They hit it with different kinds of waves, scalar, electromagnetic, and gravitational. And then step 4, the most important part, they listened. They analyzed the vibrations that came out. And this is where it gets really cool. We're talking about the sound of a black hole. So how does a black hole even ring? And what in the world can that sound possibly tell us? Well, whenever a black hole gets disturbed, say by something falling into it or a wave passing by, it vibrates. And it vibrates in a very specific, predictable way. Physicists call these vibrations quasi-normal modes, or QNMs for short. The absolute best way to picture this is to think about a bell, right? You strike a bell and it rings with a very particular note. A tiny bell sounds different from a giant one. It's the exact same idea with black holes. Each one has its own unique song based on its mass and spin. Now, this cosmic song actually has 2 distinct parts. First, there's the real part. That's easy. It's the actual note, the pitch of the ring. Then you've got the imaginary part. Sounds complicated, but it's basically just how fast that note fades away. Is it a quick ding that vanishes, or a long doong that resonates for a while? That fade-out speed is absolutely crucial because it tells us if the black hole is stable or if it's about to fly apart.
So what did they find? This was the first huge result from the paper. In every single test, with every single black hole model they used, that fade-out number was negative. And what does that mean? It means the sound always died down. The bell always went silent. In other words,
Even when swimming in a sea of dark matter, these black holes were perfectly dynamically stable. They're not going to explode.
Okay, so we know they're stable. Check. But that's only half the picture. The next big question was, does being surrounded by all this dark matter change how much a black hole eats?
To figure this out, they measured something called the absorption cross-section. It's a fancy term, but the idea is simple. It's basically a measure of how big the black hole's mouth is. How effective is it at catching and swallowing any waves that come its way? A bigger cross-section means a hungrier black hole. Simple as that.
And when they pitted the three models against each other, there was a clear champion of consumption. As you can see right here, the Bardeen black hole was consistently the hungriest. It had the biggest appetite, the largest absorption cross-section. It was just way better at gobbling up the waves they sent its way compared to the Hayward or the ABG models.
But get this, here's where things took a really surprising turn. You'd think, logically, that if you surround a black hole with more stuff, in this case more dark matter, it would just eat more, right? Well, they found the exact opposite. The more intense the dark matter fluid was, the smaller the black hole's appetite became. It's wild. The dark matter actually seemed to be suppressing the black hole's ability to feed.
Okay, we've been deep in the weeds with some pretty abstract theoretical physics. So it's time to ask the most important question of all. So what? Why does any of this actually matter? How does this math on a computer screen connect to the real universe out there?
Well, here's the bottom line. The biggest takeaway is that dark matter isn't just passive background scenery. It actively changes a black hole's behavior. It alters its song. It messes with its appetite. In short, it leaves a measurable signature, a fingerprint. And since we now know that different black hole models have different fingerprints, we're essentially building a cosmic field guide, a toolkit to help us identify what we're seeing or hearing.
And that is the ultimate payoff. The whole point is to create a library of these unique black hole songs, so that one day, when observatories like LIGO detect the gravitational waves from two black holes crashing together millions of light years away, we can take that real signal and compare it to our library. And if we find a match, we could potentially say, with confidence, for the very first time, we know that black hole was living in a cloud of dark matter.
And that leaves us with this incredible, provocative idea. For decades, we've been trying to find dark matter by building huge detectors deep underground, hoping to catch a single particle. And we found nothing. But maybe, just maybe, we've been looking in the wrong way. Maybe the answer isn't about catching dark matter, but about listening for it. By tuning our instruments to the symphony of the cosmos, the unique songs that black holes are singing might just be the clue that finally solves one of the universe's greatest mysteries.